when you're setting these things up, do we all agree that something that happens around when x equals 2, or x is less than 2, or x is greater than 2?
Yep.
Okay. So here's what we do. We graph it by all normal ways. We graph it by the normal means. We start at our y-intercept of 1, and we walk our slope with -2. Slope is -2, so we go down to right 1, up to left 1, like that. But now we have to be more specific about the domain. I'm only looking for this graph to be shown whenever x is less than or equal to 2. They're, in your sheet, they're out of sequence. I realized that after I had made those copies, I put them in order incorrectly. So I go to the x at 2, and it's right here. Now, is this has to be a solid or an open dot? It's got to be solid because it's less than or equal to. So what direction are numbers smaller than 2? Going to the left. So I go this direction. And I erase the other parts. Okay? Now I go to the second graph and I do the same thing. I start by my y-intercept like normal, -4. My slope is 5. And I think on your graph it kind of fell off the top because I had put the wrong grid on there, but you get the idea. We do the same thing. We go to where it says x is greater than 2. So I go to my x value of 2, go up to where it intercepts it. Now, does this have to be a solid or an open dot? Open. So I think if you just do that, it's okay. And then connect them, because it's continuing that way. And then you just erase out the other dots. Okay? And there's a piecewise function. You piece together two equations on one graph that are domain specific. They tell you within the domain that you only want the graph on the top to be less than or equal to 2, and the graph on the bottom to be greater than 2. Not so shabby? All right. Not neat. The fun one that has 3 of them. In this case, when you have 3 of them, how many graphs did you have on this one grid?
3.
Boy, you guys are good at counting. Sometimes. 2.5. Yes, we have 2.5 graphs, but who's counting, right? Anyway, so the first one you have x squared minus 1. I'm hoping by this point in time you guys were using the table function on your calculator. Maybe? Joe. Not it's fine. So remember when you had the table function in your graph calculator, you're able to get those values rather easily. Now, I'm going to start to shortcut this a little bit because I don't need to do the entire graph. Because in this case, I'm only looking for this graph to be when x is less than or equal to 0. So I'm going to start at 0. I know it's got to be a solid dot at 0. So when I substitute in 0 for x, I get -1. If I substitute 1 in, I get 0. Excuse me, -1. If I substitute -2 in, I get 3. 3 gets me 8, and I believe I'm off my grid now. Is that 8? I thought that was 7 for some reason. Okay. So that gives me that first curve. It's less than or equal to 0, so I'm going this direction. And I continue. I go to my next part of the graph. The next part of the graph is occurring between 0 and positive 5. So 2x minus 1. I start at -1, walk my slope. I believe that's 5 there, right? Okay. Now, remember the trick was, since this part is not supposed to include the 0, remember, we just leave it how it is, okay? You don't try to make a single, an open dot at that point. What's happening is this is descending. As soon as it hits 0, it switches the curves. All right, that's where it's telling you. The domain is telling you that it's changing, so it's not a big deal. But what happens at that 5 value when it's all the way over here at 5 and 9 or whatever this is? It stops, but is that an open or a closed stop? Where is it telling me?
Closed.
This case, it's closed because it's less than or equal to. I know most of the problems we've had is the second one has been open. You just got to just double check the read there. So all I'm going to do here is just connect these like that. And now my last part is f of x equals 3. Remember, f of x is synonymous in saying y equals. In this case, y equals a number. It happens to equal the number 3. So it is a horizontal line through what number? 3. And it's an open dot. And it's going this way. And I'm done. There are my 3 parts. Hopefully, as long as you follow through on them, it's really not that bad. Are there any of the other ones on there, the other 2 that you want to take another look at real quick, or are we all right?
I think we are A-okay.
All right. Well, let's do this. Hold on to these. These are great notes. Let's do writing equations then. Let's do this. Let's write equations.
Should we do this on paper or good paper?
I have this for you guys, so that way you don't have to worry about trying to draw these out. When it comes to some of these weird things where it's a little bit more time-consuming to draw stuff, or even write out, like word problems and whatnot, I tend to try to run those things off for you, so you don't have to worry about keeping up with writing and drawing. You can why bother now? So, I'll give you a second while these things get out. When you're looking at these grids that I just gave you for figuring out this, figuring everything out, it will tell you that assume that every tick mark is 1, and that's what I'm going to kind of keep the standard of. Even on the test next week, it should be like a 10 by 10 grid. You'll just have to count and figure out where you're at. So, when we're dealing with writing equations for piecewise functions, we need to do a couple of quick things. And the easiest thing to start with on these is to identify how many different equations you see on the one graph. So in this one, how many different graphs do you see?
I see 2.
I see correct. I almost said I see dead people, but that was being incorrect. In this case here, I'm pretty sure. In this case here, I see 2 different distinct graphs. Do we agree?
Yes.
Yeah. Do we also agree that they changed direction at one spot?
Yes.
What's that spot?
0.
Good. So now you've already identified the majority of what you need to know. You have identified there are 2 graphs, and you have identified the point at which they change. You identified the domain that is specific to each graph. So here's what we do. We know that each one of these graphs all starts out the same. Function of x equals J. Leno's face.
That is really good.
It's creative.
Thank you.
That actually looks like his face, too. Actually, I was thinking it was the other way. Like the nose.
Yeah, I see what you're saying.
Yeah, I saw it that
No,
way.
that looks like a Simpsons.
Yeah, that looks like a...
I
On Nick at Night. The Futurama, that's what it is. Futurama.
Okay.
Yeah, that's it.
Anyway, from this point here, we now have our function of x equals J. Leno's face, and we know that we have to have 2 equations. I know that the domain changes in 2 spots. X is something and x is something. It happens to be occurring both at 0. I'm not putting in any of my less than or equal to's or greater than or equal to's or anything like that yet. I know that by having these two equations, what we're going to do is we're always going to write our equations in slope-intercept form. It's kind of the general standard. And go from there. So when you're writing these things out in function notation, what you want to do is think about how you read. We all agree that we read things going from left to right, correct?
Yeah.
So the proper mathematical etiquette of doing this is as you're reading the graphs from left to right, what you want to do is you put the graph that you see first on the top, and then you go sequentially down the list. So if you've got 3 or 4 graphs, you just start from the left and you're working your way across. It's kind of like how you guys always, remember back in algebra we told you guys to put things in descending order when you're talking about polynomials? Cubed, squared, x, then your constant. It's kind of the same idea. It's the proper form. It's like when you take a sip of tea, you put your pinky up. All right?
Sure.
So now I'm looking at that first graph. It's very simple to tell what is going on here by counting the slope. Since you've got the line here, all you have to do is pick a spot and walk it. What's your slope? So if your slope is 1, what's the equation?
X.
X. Good. What's the y-intercept?
0.
0. So my first equation is x, and then I always put a comma here, because it's f of x equals x when x is something to 0. Are these numbers smaller than 0 or larger than 0?
They're smaller.
They're smaller. Now, here's where it gets to be a little bit interesting. Do you recall yesterday we had the one graph where it was the curve down, up, and then it went like that? Remember how as soon as it got to this point, it changed directions and went the other way? When it was on the curve, it stayed less than until it got to that point, and then it changed to the other line. So do you think that is going to be a less than or equal to, or just a less than? Less than. It's just going to be less than. Because the moment it becomes 0, it switches to the next graph. That's usually how you read these if you do not see open and closed dots. As you're moving from left to right, you're moving to that spot, you're approaching it, you get infinitely closer and closer and closer to 0, and the moment you hit 0 for this case, you switch lines. So this next one is when x is greater than or equal to 0. That is the common way that you do this. As you're reading from left to right, it starts, you're approaching the next point, then it switches at that point to the next line. Okay? Yes, sir.
So if 2 lines intersect, then that would make it an open dot at the point of intersection. When you have a scenario like this,
For this example,
let's say it's like 5x and then it goes to 0 and then it changes. So that's always open.
5, oh, so it's coming up 5 over 1 up 5. If the 2 lines, if they're changing at the same spot, whatever you're reading from left to right, that first one is usually the open dot, the second one is the closed dot. When we do a couple of these, you'll start to pick up on it. It's very obvious when you have that gray area where it's open and closed when they're jumping across each other, is that discontinuity. Here it's still continuous, but it's just changing direction. It's, as we do some of these, you'll pick up on it. It just takes a couple of trials here. And then we're almost done. The other graph also has the y-intercept of 0. What's its slope? 2. So what's your equation? Perfect. And you're done. You wrote the equation. It is. It's a very bad comma. I put a comma in there so that way you're denoting that your values are x when x is less than 0. Your values are 2x when x is greater than or equal to 0. It's telling you that the equation itself is stopped. The next part is your domain-specific part. Does that make sense? All right. Let's put that out. The other one's even easier. In this one, you see the jump, you know? you see how there's a jump. It's increasing, then all of a sudden it drops back down, and then it's straight across. Where does that jump occur? At what value? -2. So I know I have function of x equals j Leno space for x, -2, x, -2.
Why is there an extruding line?
When I took the first snapshot of it, as I'm dragging that across, sometimes it lags, and if I let go of it too fast, it doesn't catch up with it. It's just,
Oh,
don't worry about it.
okay. I was just thinking.
Yeah, no, it means nothing.
Alright.
Okay? So if I'm looking at just my inequalities here, this value is an open, so it's either going to be less than or greater than. But what direction is the arrow pointing? Going towards the left, so which is this going to be, a less than or a greater than? It's a less than. And what's the other one?
Greater or equal to.
Greater than or equal to. So you're about halfway done now. Now we have to identify the slope and the y-intercept. They're not giving you the y-intercept of that first graph, but could you continue to walk it to find it? Yeah. So it's going up one, right one, up one, right one. So your slope is 1, and your y-intercept is? 5. Okay. I think the trickiest thing for some of these things, as far as your intercepts might be, sometimes it might not line up on the grid. You might have to kind of fudge it a little bit to try and figure out where it winds up being. But I tend to try to make them fit for like when we get to the test next week. It should fit, all right? And then what's the equation of the other one? Bless you. What kind of a line is it? So what is it? -2. Very good, Wells. You're done. And it just so happened to be dumb luck that your domain-specific part here was at -2, and the function it was -2 as well. It just happened to be dumb luck, that's all. How to get -2 again? Remember, it's a horizontal line. All horizontal lines have the same equation, y equals some number. F of x is synonymous with saying y equals. The number that it goes through is -2.
I was talking about when you got the less than or equal to -2.
Because your domains are your x values, I'm just looking here, is that it happens to be -2. Okay? And like I said, just happened to be dumb luck that it wanted to be in it for the horizontal line again. Not super scary? All right. Well then, why don't you guys try the next couple, and we'll check them in a minute. Let's check this first one, make sure we're all on the right track. How many different lines are there on this grid? 3 of them. So we start out the same way. F of x equals j Leno space. And we have 3 values, x, x, and x. The first graph is you're reading them going from left to right. You're looking at all values that are smaller than or equal to -1. Do we agree on that?
Yep.
Okay. The next graph is between -1 and +1. So that okay? They're both open circles, so I just leave it like that. It's between -1 and +1. And then the third graph is looking at where x is greater than or equal to 1. Okay? We all right on that? All right. What is the slope of the line of the first graph? 1. What's the y-intercept?
2.
So that gives me x plus 2.
Yeah.
Slope of the line of the second?
1.
Y-intercept?
3.
Slope of the line of the third?
1.
X-intercept?
1.
Not as scary as it looked, was it? All right.
Yeah, I'm on like a different graph.
Yeah, because it's out of order, so it's like out of order.
What starts
7.
Yeah, it's like I'll have like x plus 1 at first, but you have x plus 2 first.
Oh,
It's like
if you, like I said, if you guys get in the habit of writing them as you see them, this is the first one as you're reading left to right, it's the first graph, second graph, third graph. That's just kind of how I do it.
Okay.
I mean, if you want to label it 1, 2, and 3, that might help you get in the habit of it. It's just, it's more mathematically etiquette. I don't think there's a real reason to do it any other way. It all still means the same. So, but that's just how I roll, as the kids say. They don't say that, do they? No, they don't. Let's look at the plateau.
So there are 3 graphs on this one.
There are. There's 3 graphs. I've got the increasing, the plateau, and the decreasing.
1132.
Okay? So, start it the same way. F of x equals change of space.
You make that perfect.
All right, story of how I figured out how to do brackets. In college, you have to take lots and lots and lots of math classes to get a degree in math. Go figure. There's lots of those math classes when you have, shall we say, mental downtime. You just kind of stare off in the distance, just kind of go,
Every day.
you know what I'm talking about, okay? Mental downtime. Suffice to say, it happened a lot-ish. Not really. I mean, I did find it, but there are some classes that you have that are more teacher-centered, where you're learning about approaches and methodologies. You know what I mean? Like teacherologies, or whatever you want to call it, on best practices and stuff like that. And after a while, you just kind of go. And then I just remembered being in class, doing my observations, because you have to do so many different observations and student teaching and all that stuff. And I remember watching the teacher make brackets, and I'm like, I'm depressed. And in my mind, I just tuned out whatever the professor was talking about, and I just made brackets all day. I just worked on brackets. That's all I did.
Yeah.
I had a B average in college, but I make some pretty cool brackets. So I have 3 graphs. Back on track.
I thought you were going to have 3 different types of brackets.
I have brackets to the left. I'm not as very good as the bracket the other way. So
That looks like you were trying to make it to the left, but it ended up, yeah.
I'm not as good going the other direction,
Yeah.
because you normally are writing them this way.
Yeah. Yeah, just stick to the left.
Yeah, that's kind of what I get to. So once again, we have 3 values to worry about. The first graph, it's increasing until you get to, what is that, -2? To the left of that, it's decreasing, so you're looking at everything less than. The moment you get to -2, it changes. So as you get to -2, when you are greater than or equal to -2, you plateau out until you get to +2. The minute you get to +2, it changes again to go the other direction. So you approach it with an open dot, you hit it, as soon as you change directions, it becomes solid. You approach the next one, and as soon as you get there, it becomes solid again to go the other way. Yes, ma'am?
Why is it less than -2 on one side and then just less than?
Because as soon as you get, as you're increasing with this function here, as soon as you get to this value at -2, you change graphs. You turn right. And until you get to +2, then you drop again. So as you are increasing, you can get infinitely closer and closer and closer to -2. But the very instant you hit -2, you made a right turn. Until you get infinitely closer and closer and closer to +2, and then you make that other right turn, and then you continue on. Does that make sense?
Yeah.
And these are the weirdest ones to think about because there's no that jumping gray area, if you will. It's not as easily defined and seen. That's why when you're reading them, you know you're getting closer to it, and as soon as you hit it, you make a right and hit again. So now it's just a matter of answering your question first.
In the middle graph, wouldn't they both be open?
No, because remember, you're getting closer and closer and closer and closer, and as soon as you get here, you make that turn. Once you get to -2, you're on that line.
Okay.
So when you get here, then you're at that y = 4.
But then when you switch back, oh, okay, okay. Oh, I got it.
Okay.
I think so.
So what's the slope of the increasing one here? 3. Okay, so it's 3x. And did you guys figure out what your y-intercept would be?
8.
I think it's 10. I believe it was 10. Because, what do we got here? This was 4, up 3. Yeah, 10. I say it was 10. And then, oops, I didn't realize I did that. Third time's the charm. And then the other one, again, has the negative slope of 3. And I believe it was the same intercept of 10. Yes, sir.
What?
Oh, you went like this and then, oh, you blew it up? Gotcha. You guys are all weird. It's only Wednesday.
Mucho interesante. So
No.
that's much interesting.
Yeah.
Yo capito. Hablo español.
What
To
is
comprehend?
What is yo acapito?
Yo capito. I comprehende. I think it's slang or something. It's a couple years ago. This last one is a new function. It is something you haven't heard defined by, but you're going to figure it out real quick. It's called a step function. Why do you think it's called a step function?
Because it looks like a staircase.
Because it looks like stairs. Okay? Now, the only trick with this type of problem is that you have to be careful with reading it for your open and closed dots. They could be on either side. In this case here, you have 3 of them again. You have it at 1, 3, and 5. Wow, it's really bad.
No, it's still
You know that
That's a
at 1, x is between 0, including 0, not including 2, 2 including, not including 4, 4 including, not including 6. Okay? They're just horizontal lines. They're called a step function. Open and closed dots are just telling you where to put your less than or equal to, greater than or equal to. Remember, if it's in between them, if that line is in between, it's usually going to be less than, less than, less than, less than. I don't think you'll ever write it any other way. Okay? Tonight, what I'd like you to work on then, there are a couple of problems.
Would it be 1 plus 1?
No.
One is 1.
No, what's your slope?
1. 0. 0.
That's why.
Oh, so it's always.
On this here, the homework's on page 117, 21 through 26, and then 27, 29, there's a couple more. There are 2 problems in this grouping that give you y-intercepts that don't fit on these 10 by 10 graph paper. So you only need 1 sheet of graph paper. So if you don't have any graph paper, there's some up here on your way out. That's why I wrote on there, change those y-intercepts to 10 or negative 10. And once you guys write that down, I'll show you the 2 problems that it's specific to. Like I said, this was piecewise functions. You guys did a really good job on this, and this is a newer thing for you. it just takes a little bit longer to just get in the swing of it when you're dealing with your open and closed dots. Tomorrow we will talk about graphing inequalities. It's good times. All right. You stop this, and I will show you what I'm talking about.
27, 29.
If you look at number 23 on the homework, you see how it says plus 13? Make it plus 10. On 25 it says minus 14. Make it minus 10. That way it fits on your graph. This is 10 by 10s. That's all I'm doing. All right, does that make sense? There's no reason to try and extrapolate or change your scale. Just change it. It still works the same. 23 and 25.
Can you put the